very kind invitation. Thank you all for coming today. I'm very happy to have this opportunity to visit class. I've never been here before. I've been to Korea many times in the past, to Yonsei mostly, and so this is the first time here, so I'm very happy. Like Professor Jing mentioned, I'm here to discuss some of our recent work with machine learning. This obviously is a hot topic. Many people are interested, so I would want to introduce some of our work. Our focus here is on the so-called data-driven modeling of unknown systems. So I will explain in a moment what we mean. So first, let me start with just some motivation. It's not something we really do, but this is what motivated us to start this line of work. In fact, it's a motivation for many other work we do, is that our ultimate goal for scientific computing is to make system prediction and analysis for very complex systems for very practical importance, right? So, and all these complex systems are so big that involve so many physics. And this what usually are in a model in order for us to get faithful model for the entire system. And they have multiple physics phenomena, multiple scale. And the bottom line that we have to rely on all kinds of models. These are famous equations we're more familiar with as components. For very complex system, they need to be threaded together and in order to have a better model. And the problem is that, and our traditional approach is that if we're not able to model something with some physics, let's just adding more physics, adding more equations to have more understanding, to try to cover everything. And with the hope that in the end, we'll be able to create a model that's just incorporate everything, give us good system understanding. The problem is that in my mind, we have more or less reached the so-called point of diminishing return. You can keep adding physics, keep adding equation to a model, and your model become more and more complex, take more and more time consuming. It doesn't necessarily mean your model is much better. In fact, in some cases, it's marginal better at most. And in the extreme case like this, that's what we're dealing with. And each one of these hurricane prediction model are extraordinarily complex, involve supercomputing and everything. But at the end of the day, they're all models because they are all well established, they're useful. At the end of the day, you have prediction like this. What do you do with them? And which one is more accurate? There's no way we know that. In fact, in most cases, none of them is very more accurate than the other. That's why they all exist, because they are all good in certain different scenarios. That's what we meant. And keep adding physics doesn't really buy us too much at this point, right? So, and that's brought us to what we consider data-driven modeling. I would like to make a point first is that it's nothing new. Everything has been data-driven since the beginning of science, except we tend to forget where the equation came from in the first place. They came from observations, years, sometimes decades, even centuries of observation. Then with enough observation, enough intuition, some smart people, some genius along the way came up with nice equations. That's what we deal with in the math department. We like to study these equations. Sometimes we forget they come from data and some geniuses. And I'll also make a slight point that now this is very much to us doing computing, that the equation also gets so complex that we have to rely on computer to solve them. So at the end of the day, I would like to say, this is not the model. This is the model. We have to discretize it, make all kinds of approximation. So eventually what's in the computer is not exact analytic equation that discretized, approximated. But anyway, at the end of the day, model is what's in the computer for anything realistic. We cannot solve them analytically. So this we have already accepted for a long time. Our human capability of solving things is limited. So we rely on computer to help us to solve things. And in what we call data-driven modeling is that we recognize now our human ability to come up with a model with our brain is limited. We have reached that stage. That's not much we can do. So why don't we use computer to help us this as well? Coming from data, just all the way, get a piece of computer model as the eventual things to help us analyze and understand the physics. So that's our whole point is always been data-driven, except now we're just relying on computer at more and more places, which is something we all know, how machine learning takes over. Think about ChatGPT, things that can never be imaginable, right? All right. So having said that, I want to start with, now we're in the math department, well, let's be a little more concrete. What we mean precisely by data-driven. This is particularly for dynamic systems. Things evolve over time. So I'm going to assume we have measurement of data, some history of data. Over a certain time, K would be some, a piece of history data, and you can have little superscript I different piece of measurement data over time. Right? That doesn't really matter. And you observe temperature or something at different stages, but over time. And what we try to do is that using this to come up with a model. I don't want to derive the equation. We admit I cannot derive the equation based on this data. Let me just get a numerical model that based on this data so that this model can predict things. It's a recursive model. Knowing the current would let me know the one step in the future, and I can recurrently use this to predict everything. So with the hope that my model prediction X with a subscript is a good approximate to X of T. This would be a true solution measured here. Right? So that's our goal. This is in fact the goal of all numerical method. Our numerical model should match the truth at a certain point. Right? So that's what we meant. That's the whole setup of this talk. With a few remarks that which is important. May not sound important now, but at some point, when we create this model for X, we will try to avoid using time variable T explicit as much as possible. In fact, I would say you never use this. Why? Because if you use time variable as a variable in your model, that means in your training data, what you observed, you have stored T in there. It doesn't matter when you store T, even I wrote T here, but we will not have T. We only have X at N as variable. We do not want to store time. Time will never be modeled because when you store this time, that when you do prediction, you always go beyond that. But then if you have T as a variable to model, for future prediction, that will become extrapolation. Doesn't matter how much time you observe, you always want to predict much more in the future. So having this would prevent you from doing that. Another very big assumption or a common occurrence that this is some physics, some variable, some very complex physics. We are not able to observe everything. Think about climate. You can measure the temperature, pressure, density, but an entire system for climate may involve a million variables. We never will be able to model, but we can only measure a few. So this is another assumption that, yes, we only can observe what we can observe, and the things we observe cannot, mathematically speaking, form a closed system. Again, back to temperature, climate example, if you model temperature and the density, you know these two cannot create a climate model closed by itself. In order to close the system, we probably need another 10,000 variables, which we are not able to do. But this is what the situation we're dealing with for all the complex systems. Right? So having said that, I want to start with an example to sort of more or less emphasize this part. So let me give you, before that, let me give you a basic setup. In all this talk, I will give you all kinds of numeric examples. In all the examples, we will sometimes have the true system in the background. All right, so that we know that the only way this is useful is that this will be used to generate the training data and then to validate. So knowing this true model in the background in no way whatsoever to help us the method. It's just the way to validate things. The method I will discuss is so-called flow map learning method, and just have the name. Everything has a name these days. So FML. You will see in a moment why this is called. It's not really, it doesn't connect to machine learning. It's just a methodology. Using deep neural network is a way to implement that. You don't have to, but in many cases, this is the most flexible way, neural network, but you don't have to. Everything I present today is not a magic of deep neural network. We are just using deep neural network to try to accomplish what we set up properly mathematically. Right? Everything is about how to set it up mathematically. For all this validation, we'll assume there's no noise. Having noise just reduce the accuracy of our model. So here, just for testing, for now, we're not getting noise. So let me start with this example. Right? This is so-called, it's a more or less a math biology example. It's very close to the study of diabetes. It's how we understand the dynamic of insulin after that based on glucose level. So insulin is what diabetes patient need to inject, right? So, and it's complex dynamics, right? We know that it depends on individual many things. But let's assume all we have are the data that I can measure, which you can. There's a lot of data you can measure in terms of diabetes. You can measure the insulin response after injection for a short period of time. There are 15 points here, actually 16 points, 0 to 15. Exactly, this is a setup of the example. But this response is based on so-called glucose level. It's a baseline level. It's a constant of this individual. So the individual, if he or she has a meal or after exercise, after wake up, this level would be different, right? So then you inject insulin, the insulin had start to respond, and glucose will change, everything will change. But that's the initial condition for this glucose level, and this is the early response of insulin. I can measure that. Suppose I have a good measurement for very early response. I don't have a long time dynamics. We can measure this a lot for certain individual. Let's just measure all this for different baseline glucose level. After having deal this level, the insulin early response like that. Different level, different early response. These are all exactly 16 points here, right? Based on different G0. You can measure all these things. So we ask the question, can I understand, based on the different glucose level, how the insulin respond for long term? We only can measure this for short term, right? And obviously, this is a problem that's very hard to study. It depends on all kinds of other things, all kinds of systems for the individual chemical reaction, everything. But that's all we have. This is purely data-driven, nothing else. So let's do something. Neural net. Neural net is magical. Let's just try it. So I'm going to try this in a very stupid way. I'm going to take this piece of data, early response of insulin, and based on glucose level constant, I'm going to throw this glucose level in here as a node, as an input of neural network. I'm going to take this 0 to 16 points. I'm going to take the first 15 points, throw them here, 0 to 14. Right, so my input would be glucose levels constant and the early response one shot. Then at the output, I put a deep neural network in between, fully connect, nothing fancy, the simplest neural network. And at the output, I'm going to throw the last point here, try to match it. This is where I compute so-called mean square error. So basically, what I'm enforcing that, knowing this parameter, knowing the early response up to 14, I want to enforce neural network to give me the last one, 15. We have the data, I can do this. We have many of the data, we're going to feed this, all this is a big data problem. So I train this network, mean square error. At the end of the day, I create a model that given a glucose level constant, given the first 14, 15, I can predict the next one. Then I can, after predict, neural network will give me this number, try to match this. After this, I'm going to move this to here, slide everything backward. So I will create a map that based on 15, give me the 16th response. I can keep moving forward. Then I will be able to predict long future, as long as I want, not restricted to the early response. All right. So that's almost like a multi-step time integrator. You can go forward in time. The question is, of course, how good this is. I mean, you can always train neural net, get something. Is it any good? So let's test this, right? So after training the network, we're going to fix it, not touch it. We only execute the same models. The network is, as I said, is a piece of computer code. It's a model. I call this a model for my insulin response, right? That's all. These are a few test cases. They are all exactly the same as the measurement training data, given different glucose level, the early response up to 14. Let's get the 15 and so on. So I'm going to show you the first top one here, and at different level, everything after dot, after circle would be the network prediction. This is the initial condition that 15 after 14, and we keep going on further after much longer time. This 20 non-dimensional line, this is 47. You can see here, I call the truth. I tell you in a moment what truth is. The neural net predicts very, very accurate the long-term dynamic. Different glucose level dynamic becomes slightly different. It's again settled down to steady state. Again, everything after dots would be prediction, no data anymore. And different glucose level, very accurate. And then all of a sudden it become different glucose level here, it become a periodic state. It doesn't settle to steady state. But again, network somehow knows based on different initial response, which there's no indication you can see whatsoever if it go to steady state or periodic state. But the network would get to this, right? So once I have this model, I play God mode. Now that I know exactly how the insulin would respond based on early measurement, and based on these parameters, I'm going to play God mode. Just keep executing this model, try to study its phenomena. One thing people know is that the eventual dynamics, steady state or periodics, depend critically on this initial parameter. So I'm going to keep executing this, find this, and people measure the final max and mean of the stabilized response. If it's steady state, max mean would be the same point. If it's periodic state, max would be up here, mean would be down here. Then you can plot this kind of bifurcation diagram. Different glucose level, this is steady state, max, mean are the same. And here would indicate this periodic state, the amplitude would be within this. And it becomes bigger, wider amplitude, still steady state. And all of a sudden, you return back to steady state. It's an interesting dynamic program, bifurcation behavior. People study this quite well, but this is by a machine learning model and knowing very little, knowing only a parameter and some data, that's all. I can also do these things people do. What if my baseline glucose levels, initial one change here, like having a meal get higher, and having dessert even higher, exercise, whatever. So the insulin response would be wildly different. But anyway, again, we have very, very good measurement. And in this particular case, the accuracy of the machine learning model is almost identical to the truth. So let me tell you what truth is. The truth is here. I don't really have real data. The truth would be what we measure from this particular individual measurement. I don't have that data, so in math department, I replace the person with a mathematical model. In fact, fairly simple one. There are several mathematical models study this phenomena. This is more or less a well-known one, reasonably complex. So we took this from a textbook, math biology textbook, and all the parameters has 4 variables, 16 parameters. I put all the parameters there. This is what I use to generate this early response of my insulin response. But the neural network knows none of this. You only see the early response. You only see this initial parameter and the early response of this. Then it's able to predict long-term behavior of I. It doesn't know anything else. So it's kind of surprising because, again, we effectively create a scalar model that has bifurcation dynamics that can replicate a sub-variable in a much, much bigger system, even though this is not a real individual, but this is quite representative of what the capability of this modeling approach. So it is possible to build a very accurate self-closed model, even though the variables would never form self-closed mathematical system. So this is what this method can do. So now let me explain to you why this works, because as I said, we throw this into neural net. It's not. Right? So this is setup. Knowing this, I want to create a model. It's not we random try this and find a neural net is so magical, give us this. It's about 5 years of work, step by step, and with different breakthroughs in our development of this methodology that glucose insulin response example is not in any of these papers. When we tried the paper for demonstration purpose, we knew there's no way it doesn't work. It has to work because all the maths are there. In fact, that example turns out to be an easier one to do. There are a lot more harder examples we tried in this. So let me go through a few critical development in this to explain to you why this works, because it sounds like it's something that cannot be done in the past. Right? So just one quick word about neural net, in case some of you are not familiar with. In our setting, we are not using any magic of neural net. We treat neural net as nothing but a mapping. It takes some input, takes some output. Anything in between is by training, by data, is try to create a mapping from input to output. This would be R8 to R4. That's what neural net does. You can have all kinds of structure in between. At the end of the day, it's a mapping. Right? Whatever structure is happening inside. Right? So in this case, 4 to. So in our case, that's all we use. There are all kinds of things. We use none of this. We just use fully connected, very simple one. All right, so let's see why this works. We'll start with a simple system. Right? Suppose I have an autonomous dynamic system, vector system. It's autonomous, there's no T here. And suppose I do not know what F is. I don't know the equation at all. So, but what we do have are the measurement of X, like we said before. We have a measurement of X. the entire state variable of some trajectory. We have that. Right? So the reason this is called flow map learning is that we are not, there has been quite some work to try to use data to recover the right-hand side, called equation recovery, and with some polynomial sparse recovery, and even some neural net, we don't try to recover equation. My underlying reason is that even if you recover the equation, so what? You still have to discretize it, try to solve it. Why don't? So at the end of the day, having equation doesn't help much. As I said, the right-hand side eventually is a piece of code. So let's just go that directly. So we try to find the flow map. What is flow map? It's a very simple thing. Flow map just said knowing equation, it's a map between the solution at two states. Right? So if I have a solution at t0, may not be 0, it's time, and I have solution at t, the mapping is just this map solution from t0 to t. In this case, for autonomous system, time doesn't matter, only the time difference matters. So whatever time difference between these two, that's the map. And this map is a simple one because this map is nothing but of the same dimension RD to RD. If my state variable is D dimension, it maps whatever at the D dimension to next another D dimension. And here we are going to, from our measurement data, I'm going to take the neighbors. They're separated by a very small time step, whatever the measurement dictates, called it delta or delta T in numerical analysis. And since time doesn't matter, I'm only looking at time difference. I'm going to look at my measurement two solution at two time level in consecutive to each other, right? I'm going to call this one x0, the other one x delta t later. And this flow map says this is the flow map parameterized by this delta t. I can pull a lot of this from my measurement because time doesn't matter. I can treat every pair as starting with some initial condition and evolve by an unknown equation for one step. We have data here, we have data here, and that's all we need. And let's use neural net to map something in between. So all we are trying to do is try to find a function map of RD to RD. So like I said, and they are also even connected. You can, if I know the equation, you can integrate them, do some mean value theorem. But anyway, the map in between, you can even bring the x0 to here, so that what's happening inside is the difference between. So you can map this to that directly, or you can try to map this to the difference and add it back on. There's no difference, but pulling this x0 out of it to map the difference is a well-known idea in neural net called ResNet. Mathematically, it doesn't do anything. It just maps the difference, add it back on. So it doesn't do anything. Numerically, it helps. Right? So we started this work by using the idea of ResNet. We found it useful, but to be fair, later as we do more and more work, having the ResNet structure doesn't really, it's not important. You don't have to. So, but anyway, let's stick with the ResNet. So I want, from my measurement data, I'm going to put a pair. So current, next, current, then you can put a lot of. So you have lots of the trajectory. Each trajectory you can put lots of pair. And I will feed input here. For each pair, the input here, and the output will be the next in the pair. Right? So I have lots of that data. Use the ResNet, just bring the one here. We can train a network to map this. That eventually give us a predict model. So knowing the current step, I can keep getting the next, and that's all it does. Right? So nothing fancy here. Again, like I said, using this to map this is not essential. It's a function approximation for RD to RD. You can do this with polynomial. You don't have to use network. So this would be example of rather a sort of extreme example of a dynamic system with 4 variables. So we'll have R4 to R4. If I have measurement along the way, I'm going to pull every two pair from here. This will be my input in my network. This will be my output. This will be my input. This will be my output. I have all these things to train and to learn the model. And this will be the response of this. So my postdoc back then for this example, a rather industrial example, I want to make a few important remarks. Like I said, this methodology to find this mapping. Now, this would be the mapping. Now, in this case, I write in a more general way. There'll be none of this. So just xn to x, right? So m would be 0. Like I said, you don't have to do neural network. You can do polynomial. In fact, this plot are produced exactly by polynomial because it's R4 to R4. 4-dimensional functional approximation, we can easily do polynomial. You kill it with absolutely fantastic accuracy. You just kill it. Why? Because the mapping between two states from one dot to another is extraordinarily simple map. In this particular example, the delta t is 10 to minus at 1 nanosecond. think about anything separated by 1 delta t. You can do Taylor expansion is 1 plus something. It's a very small change. So the mapping you're trying to find in between is a very, very small mapping. I mean, -1 is a very small mapping. It's also very smooth. It's an integral of your equation over 1 step. As a function, every equation we deal with, in almost all equations we deal with, are extraordinarily simple. So let's not be confused with the equation as a function or the solution, because equation as a function are always very, very simple. Here in this, linear, 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 one term, weakly nonlinear. As a function, this is a very simple function. So one step integral of this function is a very, very smooth function, separated by a very, very small time step. We are really approximating a very mild function. So a polynomial, if you can do polynomial, will kill this right away. However, this little bit nonlinearity over long term would give us very wild behavior as a solution. So if you think of this as a solution, a function of time, it's extraordinarily difficult to approximate this solution. That's why I said in all methodology, do not have time variable as your approximation, because then you end up approximating this function. It's impossible. No method can get this function accurately. But here it's so accurate because this method doesn't even try that. It's only try to find a map that knowing here, I will go here. Knowing here, I would go here. Knowing here, I would go here. Very little change. If I get this right, over term, long term, it will get me the right behavior. Every step, you just need to learn the small step change. And the one step change would eventually give you the correct function over time. But don't try to approximate this as a function of time. It's a dead end. It's because it doesn't matter how you map your function of time. This is 1,000 steps. What if you want to go to 2,000 steps? Your function breaks down. You cannot move beyond. But this, you can keep moving beyond because I'm just very, very short-sighted. I look one step, next step, next step. If I take my every step accurately, I know it will lead me somewhere accurately. I just don't try to model this thing as a global function. All right, I hope I make this point clear, and I will show you more example why this is the very critical thing in this type of work. Right? So let's make this more interesting, because if I observe everything, it doesn't really do much. Like I said, in most example problems, we are not be able to observe everything. So again, let's say I have a dynamic system. I don't know the equation to start with. That's difficult. Make it more interesting, more difficult is that in this X, I can only observe a Z, the subset of it. All right, whatever D can be 1, 2 in some high dimensional space. The rest variables, I have no data. In fact, you probably have no idea they even exist conceptually, because all you know, I see this, that's all you see. All right, so this is what I have, trajectory data. I'm trying to, so we ask questions. So can we create a model for this? With the understanding, I don't even know the closed system in the first place, but I just want to do that. All right, so turns out this can be done, mathematically speaking. There's so-called well-known so-called Morris-Zwanzig formula says exactly that. Having this autonomous system for subset variable, there exists equation for the subset variable sort of self-close by itself. Knowing Z, it only involves Z, and a random term that depends on initial condition that involves missing variable. These are the missing variables. But anyway, this is usually treated as a random term. It doesn't really matter, right? So this exists. The problem is that this is an exact formula. Right? There are two major problems. A is that this first, so the bigger problem is that nobody knows what R is, K is. It's more or less like existing result. This thing exists. There's no way to derive this. Even if we know the little f in the complete system, there's still no way to derive this. In fact, that has been an active research field to try to derive this, knowing this. We are even one step less than that. We don't even know this stuff. So knowing this formula is completely useless, but still is useful. We're going to use this to motivate a way to design a neural network. So let's observe this integral. Right? This is more or less okay. It's a Markovian term. The term depends on current time, even though we don't know what R is, but fine. Our early work is that we don't know right-hand side. We can try to model it. This is the troubling part. This is so-called memory kernel. If you look at integrand of S from T, so T, think of T as current time, I want to understand. The integral of S from 0 with T minus that is current time. To T, this will be T minus T will be 0. So this says my memory would go all the way backtrack from the current time to 0. So it means that if I want to have this equation exist, I need to know the evolution, the data of z from the beginning of the initial condition, the beginning of the universe, right? So that's what makes this equality. So, but it's not possible. Nobody knows what time the kernel is, even if we know the little f. So there's no way to derive this, but let's try to motivate us this. So we're going to make two assumptions, very, very mild, reasonable assumption that satisfies for almost all systems. A is that for this memory integral, we're going to assume, you know what? The memory is finite. For any system, in order to know what happens at the current time, I don't need to go back to the beginning of the universe. I may need to go back 1 day, 5 days, in climb the model, maybe 7 days, that's enough. Anything occurred even before that has very no effect on the present, which is the case for almost all systems. So, which means this is backtrack to where? To the beginning of time. I'm going to, so for this integral, I'm going to backtrack from current time backtrack to this, not to t minus t to 0, to t minus some finite number, is what we call the memory length. How long is the memory? I don't know. For any given system is different. You have to test, do some numerical testing. It can be done, right? So, but anyway, there's a finite memory. For climbing the mountain, this will be 7 days. For some other system, can be some shorter time. So this integral, if I truncate it here, it will be almost exact, right? This epsilon can be very small. Anyway. Second, now that I replace this integral to a finite integral, it doesn't go all the way to this. I'm going to say for this finite integral, I can find stencil data in between this interval, the memory interval, to approximate a function of the to approximate integral. This is always true. I mean, if you know this, then you can do trapezoidal rule. You can always find a way to approximate integral with good accuracy. Here, we don't even need to specify what we use. We just say that exists something to approximate integral. That's all we need. So having said this, let's put this all back to Moritz-Zwanzig. I'm going to have a approximate Moritz-Zwanzig because we had made two mild assumptions, right? So this Moritz-Zwanzig at current time, let's call it Tn to be more precise, would depend on something at Tn, and then this whole thing will be replaced by this, depends on some function of everything happened in between this from the current time. I'm going to backtrack 1 step, 2 step, whatever. This number of steps have inside the memory interval, all right, for this integral. That's what we use. So like I said, this mild assumption makes this approximate system. This is tractable because why? So not solvable, not knowing the equation. We don't know what R is. We don't know what M is, but that's fine. That's what our starting point. But all we know is that to march from current to knowing the derivative, we can march forward in time. All I need are just data of current time, 1, 2, 3 stop, whatever steps in between the memory length. So that's our overall scheme. Right? So this would be the memory. If you do neural net, it would be the structure. So I need data for the current step, 1 step back, 2 step back. This will be an example that your memory only requires you 3 terms. Your memory is not very long. You just need 2 extra terms here, but it will map the future. You have enough data. I'm going to feed this in here. I'm going to feed the next one as when I compute the error exactly like I did in the insulin example. And this is the basic of that work. And once you have this in principle would work because this comes from very motivation from very rigorous mathematics. I want to caution that once you train the neural network, it's natural to extract the formula here is not possible. It's just not. Everything is messed up. It's a good motivation, but if you want to backtrack, neural net does something on its own, it will not be doing anything like that. But anyway, let me show you some example, right? So this will be tough. All these examples are tougher than the insulin example we did. Insulin example was, in fact, the easiest one. We did 1 training is done. This, we have to, be careful with the parameter, everything. So let's assume I have a linear dynamic system, but I don't know what it is. It's the dynamic system of 20 variables. My matrix is 20 by 20. I know none of the matrices, the entries, the 400 parameter matrix. I have no idea what they are. But what I do have are the measurement of the first trajectory of the first 10 variables. I don't know anything about the next 10 variables. In fact, as far as we can tell, this system could be missing 10 million variables. Doesn't matter. All we see are the 10 variables. It's like if I split this into 2, I have no idea what happens here. Just to make a point, this 10 variable cannot close by itself. It requires dependency on the rest of the variable. So it cannot. It's not self-closed. So anyway, so now we're just going to use pieces of this, a little bit of memory piece to train the network. How much we need? The memory after testing this, memory is 0.6. So we just need to observe 0.6 of evolution of the 10 variables. We observe enough, train the network. Then let's do prediction. Everything is moved. I give 0.6 as the initial condition. The network will take over much forward in time. This is what it looks like for network prediction. The red, the truth, if I compute from the real system with all 400 parameters compared to this would be x3, x6. That would be the comparison for two. They all look similar, but this is time marching to 150, way beyond what we observe. You only see 0.6, but it's able to go to 150. I mean, the accuracy is there, so nothing indicates to zero, everything. So anyway, so this turns out to be linear system is very difficult to solve very accurately. This is an example we really was happy eventually to achieve. Let's make this slightly more interesting. In fact, a nonlinear example would be some kind of slow, fast, very chaotic system. The true system, again, the true system is what we use to generate data, is this, has 3 slow variables, 1 fast variable, depending on epsilon. Right? Mathematically speaking, if I take epsilon to 0, you can do homogenization. The slow variable would follow this, right? So let's assume we're not able to measure the fast variable. They go too fast. It's very hard to measure them. Let's assume I can measure the 3 slow variables with data, and I want to create a model for the slow variables only. Again, they do not close by themselves. They depend on y. In the limit, there's a closed system of epsilon go to 0. It's closed by itself. But when epsilon is 0.1, the slow variable cannot close by that. But we observe x1 to 3 of memory length 1.2. Again, very short. We train the network for a model for x1 to 3, not knowing anything about y. And this is the model prediction of up to 400. I didn't even plot the first 200. It's 200 to 400 because I put in the same plot. Everything looks random. In fact, it's not. This is a deterministic chaotic system. You can see it's not random. The network prediction is the red one. The truth from solving this, knowing y and recording x1 to 3, this x1 would be the black. You can see visually red and black very well. Just for comparison, this is a mathematically closed system. It's not accurate in this case, but it's reasonable. And it's the green one. You can visibly see that the error is bigger at 400. Then if we compute the error of the mathematical approximation and our neural network approximation, this would be the error evolution of all 3 variables in L2 of the neural network model up to 400. Again, you only observe 1.2. And you can go to 400. The error is here. And this is this model. This is the typical model error behavior we see for dynamic systems. Or any approximation method will have error grow over time for this. And this is much smaller, much more stable. It doesn't really grow. This is one of the issues we have seen over and over again. The neural network model has very interesting and many cases surprisingly better behavior in terms of stability. We have no way to analyze this because we don't know the neural network. The detailed neural network is very hard to do analysis. We just take them this property. All right, let me make this even more interesting. A famous example in this equation recovery is people like to solve chaotic systems. In fact, let me say chaotic system is easy to solve. Anyway, linear systems are hard. Let's do this. So Lorentz, this is the truth. I'm going to make this harder. So let's assume in this example, I only observe X and Y. I have no idea about Z. There's no data. I don't know. So let's observe X and Y trajectories of length 0.1. Okay, teeny tiny. Observe many of this. I'm going to train a neural network based on 0.1 can go forward in time. This will be the neural network effective 2-dimensional model for X and Y only. Neural network doesn't know anything about Z. And starting from here and give you some kind of this very much like what you observe for chaotic system. This is the truth after solving the 3-dimensional system, but plotting the 2-dimensional phase diagram. So this is truth projected on 2 dimensions. This is a 2-dimensional model, numerical model. You can see they're very close. In this case, we don't have good point-wise error because it's a chaotic system. No method can have point-wise error bounded over long term. So they look qualitatively the same. Let's just, based on this, we're going to compute these few measures for how chaotic the system is. This is correlation length, approximate entropy, Lyapunov exponent, you can see the number, they are reasonably close to each other. This number are very sensitive to the trajectory length. It's a numerical issue. So it's very hard to get this number very close. It's not really the error of the solution. It's just hard to compute this number numerically. Anyway, let's make this even bigger. I have a Lorentz 96, which have 40 state variables. Oh, by the way, I mentioned here, we also tried just observing X, right? Try to predict the future. I didn't plot this because one-dimensional X is there's no phase portrait. It's just a curve. So you can do that. You can also get this thing very close. This is interesting at least to visualize for. We also try to imagine Y and Z and they all work equally well. Anyway, 40-dimensional Lorentz system. Let's assume I can only measure 3 variable x1 to 3. Right? They're all fully coupled, right? So x1 to 3. Let's create a 3-dimensional neural network model that I forgot what the memory is. Again, it's very short memory. I forgot this. Anyway, and this long-term phase portrait of the neural network model of x1 to 3. There's nothing else. X1 to 3. This is a little bit messy. This is the 40-dimensional system. If I put x1 to 3 variable, do a phase portrait look like this. This is it's very hard to see anything, but you compute this measure, they are reasonably close. Again, this is a hard number to do. They're actually reasonably close. You look at the stabilizing probability density invariant manifold, and you see they are reasonably close to each other. Okay, so, all right, so let me skip this. So let me give you a little bit summary of this. So if I don't know the system, I have data. If I observe all my X, it's a simple thing. All I need is pool data or reorganize my trajectory data to pairs. And you can throw Xn in here, Xn plus 1. You can get a lot of this. You think about network training needs a lot of data. Not really in this approach, because let's say I need 10,000 training data. I need 10,000 pairs. It's just 10,000 pair. Effectively speaking, is 1,001 the length of trajectory. Sometimes you do a simulation, you easily do 10,000 trajectory, just one simulation. So this sounds like a lot of data. It's actually not very small data. But anyway, that's how you train the network. You can do rest that. That's fine. If you only observe partial of it, only Z, based on this motivation, you just need this model. Right? So this is the model here. All you need is that you have more input here. You need to observe a little bit longer and put the input here, get the output here. How long is this? You have to do numerical testing. Right? Keep increasing this until your solution stabilizes if you don't know the truth. When we know the truth, we can compare it. Right? So that's the essence of this approach. Like the example I showed you, they work quite well. And let me skip this. We can also work with external input for control. If you observe something here, based on some external input, if you can observe your response, and you can train the network to predict this. If you observe a completely different input, that this input for gamma is never seen here, ever, ever, ever. But you can do some approximation to do that you'll be able to do this kind of prediction with extraordinarily high accuracy. In fact, this is a 6th paper. There are a few steps. Time is limited. If you're interested, we can do this later. But anyway, it's all based on one step, looking at everything one step, not model things as function time. That's a key thing here. Right? But anyway, let me just show you. Okay. This will be natural structure, but anyway, let me skip this. This will be an example that we train this thing. Our input data would be on very mild polynomial, small polynomial. If I observe my trajectory on different polynomials, and then let's do prediction. If I have a new input, I don't know this equation. I don't know anything inside. All I have is input and X, input and X. Now for prediction, if my input is something completely different, this is not polynomial. This, in fact, is almost like input. And the prediction is that. So this method is very powerful in handling that. It takes a little bit math to get there, but at the end of the day, we're able to create this method that based on what you observe input, you can predict completely different things in the future. But anyway, so I want to speak just for a moment about PD, because obviously this all works well. What about PD? Just a few moments, right? So PD, let's just say I have a PD, but I don't know what it is. But what do we do is that I observe my solution at a set grid that we always do. So suppose you have finite difference, you observe your solution at these grid points as a snapshot at different time. I'm going to write. So every observation on grid points is just one big vector. If you have 1,000 grid points, this will be a vector of length 1,000. Right? It's just one big vector. and I have this observation over different time. That's my trajectory. It's the exact same setting as a dynamic system. So nothing is missing. If I'm observing all my U's here, no missing variables. Oh, I just need map one-step mapping. I don't even need a memory. Let's do that. So it's autonomous, time doesn't matter. So put this current as input, put this as output, connect a network in between should work. It's just a dynamic system. The simplest case, the flow map learning I discussed, except it doesn't work. Right? It does not, I shouldn't say it does not work. It works to some way, some degree. We were, in our group, we are very, very rigorous about numerical error and numerical simulation and errors. It just kind of works. So we tried all kinds of things. For more than 2 years, we tried many things with no less than 10,000 testing. I'm not joking, no less than that. And at some point we realized, okay, we cannot do that because this is not dynamic system. In dynamic system, I have this vector and vector in between. Vector can be anything. It's just a vector, x1, 2, 3, 10, doesn't matter, right? But this is not arbitrary vector. This solution in a physical space, it has smoothness, it has regularity. It's not arbitrary x component, right? So there's something needs to incorporate some physical structure because the operator here to enforce this before we map it. So we tried convolution because convolution naturally would give you some structure. It kind of works. Okay. After a few thousand results, it kind of works, not entirely. So we eventually gave it up. Right? So just because it doesn't really work accurately on a consistent basis, we were forced to try something just brand new. Let me show you what we tried. Again, everything's based on math, not neural network structure. But this is one we did develop a network structure based on math. This is some PD with some differential operators, with some unknown things to put everything together. So operator, differential operator. Suppose I can do OLAP forward. I do the simplest method, OLAP forward. What would you do in OLAP forward? You just, my numeric solution, you count the step. Next time on every grid point, you would use your operator here. In between every differential operator would become, if I do OLAP forward or any numerical method, this becomes a differentiation matrix. In OLAP forward, for example, second derivative, you get 1, negative 2, 1. Find a different negative 1, 1 divided by 2 delta x. So it's a differentiation matrix. In spectral method, you have different matrix. Every operator is a, if I do numerical approximation, is a matrix and connect together. This is my numerical scheme. This is, if I know the equation, I can do that. OLAP forward will not be stable. In many cases, it doesn't matter. I only look at one step, right? It's one step. That's our motivation. So now I don't know the equation here. So I cannot write down these matrices. I don't know this operator. I don't know L. I don't know this. What if I don't know? Let me replace all this by network. I can just do that. So based on this, I claim, so this is OLAP forward, come with its one-step truncation error. I say I can make all this nonlinear operator. I'm going to do no worse than the OLAP forward. I'm going to write that exists the scheme like this with some operator, this, with every D replaced by a nonlinear operator, and this scheme would be no worse than this. Its error would be at most as big as this, most likely smaller. Of course, it's a trivial result because why? I can prove this just by putting everything back as D, and that's my thing. If I make this arbitrary choice, I can always make it better, right? So anyway, so it's a trivial thing to think about, but this is what our motivation. Now I say this, again, not knowing this, it's just nonlinear operator. I don't know them. I don't know that. Let me replace each single one of them by a network. I train them. So this is our network structure. This is the nonlinear scheme I have. So I'm going to create a network structure, giving the input VKN, a big vector. We should have physical structure. I'm going to put a network here, this to represent F1, and put another network in parallel to represent F2, and then the next one to represent Fj. I don't know how many J's, but I'm going to put a few there. Then I'm put a network here, cut across it, operating component-wise on everything to represent this, which is L operating in my PD. Putting all these things here, I'm going to map this back to, with a +1 here, this delta T +1 here, this, my output would be here. Now, if I have enough input-output map, which I do, I can train a network like this, as opposed to connect them with a simple, fully connected network, or do a simple convolution if that convolution doesn't matter. Well, in fact, this is almost like convolution. The convolution is almost like this without this layer. This is a critical layer. If you don't have this, you will not be able to enforce continuity here. That's what we observe over and over again. When you don't have good continuity, regularity, eventual stability kills you. I mean, just no way around. So the model is not all of all. Everything is based on this, but like I said, other things don't work. Let me show you some example. This is a simple one. This is the simplest PDE, but we all know in numerical math, it's the most difficult to solve because no error can be hidden here. But anyway, I observe lots of this data to train this network. This would be, my data is one step separated by delta t. That's, so your observation is the evolution of one delta t. In this, most cases, our delta is 0.1. But then you do long-term prediction. This is t equal 2, 3, 4, all the way to 20. The linear wave equation, you can see they're very close. So this is one thing also we observe with the network model. It has remarkable dispersion property. Numerical method usually at 20 with so visible diffusion and dispersion. Means the phase would be mismatched and the amplitude gets bigger, smaller. This network has very remarkable property enforcing this. We don't know why, but it just works. Linear advection equation, this is easier, and because it's easier than advection. This is just to show you the method doesn't care how your node is distributed. It can be some randomized node. In fact, we even permutate the nodes. There's no connectivity of adjacent node. They are randomly permuted. It works in which if you random permutate, convolution doesn't work. Convolution needs to know the neighbors. Force order PD works fine. Just to show you, yeah, it doesn't need to have just differential operator, can be integral operator. Eventually, this will be some nonlinear operator. So do this integral equation. This effect make this a non-local problem, works fine over a prediction. This will be the interesting example, tough one, the Berg's equation, right? So I will observe one step of solution evolution. How did we generate the training data? We do some random sine cosine function. I mean, arbitrary wave number. So it's very smooth. We solve this smooth function by one step. It is still smooth, one delta t, no shocks whatsoever. But you observe any of this, give a new initial condition, let the model evolve by itself over longer time, it will find the shock at the right time. In fact, quite accurately. So this is something I would like to say. This method, you don't need to see the physics to predict the physics. In your training data, you don't need to see what you want to see. In fact, my incident example would be the same thing. You never see in your training data, never have bifurcation, steady state, but it will get there. If you do very short-sighted one step correctly, it will get to the correct physics. Just make it complicated. I can say, oh, what if I don't observe the entire domain? I only observe 40% of the grid points evolution. I trim it. This would be long vector. I only observe partial of it, and we need the memory. The network gets the structure earlier and also involve memory. You can still do prediction. This is not as good as before, but 40% of domain shock evolution, I think is reasonably good. My student at the beginning was saying, this is too bad. Should we tell people? I said, no, it's not too bad. This is, no other method can do this. Let's to start with that. And this is not too bad. Anyway, two-dimensional example, just for demonstration purpose, unstructured grid, you can do that. We can again make mixed variable, this for this physical Nagumo equation. If I only observe V, not W on this grid, again, we need a memory over long term. And the solution would actually just for V only properly sort of periodically over the vertical domain. So after 50, this prediction, this reference looks reasonably close. And it's two-dimensional example, mostly just for demonstration purpose. The accuracy is quite acceptable. So with this, let me conclude. So I've discussed this flow map learning methodology. Like I said several times, it has nothing to do with neural network. It's how everything I discussed here is all about how to set up the mathematics properly. And then you know the map should be this and that. Neural network is a way to implement the map. If the dimension of the map is not high enough, do polynomial, you kill it. Right? So, but unfortunately, in most cases, especially in PD, the dimension is very high. So neural network is only a viable way to do high dimensional functional approximation. For students who have done this thing, you know how unpredictable the result can be when you train that. Same training data, same parameter. One day you train the net, you get the result pretty good. The other day you train, it's not so good. And you just have to so-called terminology cherry pick sometimes. So this is one thing. So this is in our group, we try as much as possible not to cherry pick. So we train the network to the extreme to make sure they are reproducible. So I think the word is reproducible. So we're in the process of this. Most examples I showed today, we're going to publish all the results on the web that include how we based on true model, how we generate training data, the description. But if you're lazy, you don't want to do it, we will have a training data set to publish on the website. Just as it, you can download your training data based on the training data. And if you are lazy now, we'll have our training result there. You can just execute. More importantly, we're going to publish the data that we use to plot the plots, like in the paper, so you can replot the plots first. Then you can do your result, lay on top of each other to see if you get better or worse. Right? So that's one thing. That's how much time effort we spend to make sure every result are reproducible. We're going to publish even the data to plot the data. All right. So with this, I think I'll just finish here and thank you for your attention. I can entertain some questions.